current biasing before as well. The idea is to bias, for example, over here, an NMOS device, an NMOS common source circuit, which is biasing a constant current source. The idea is to bias this with a current source, let's say IQ over here, and then according to this IQ, the gate to source voltage, the gate to source VGS, has to adjust itself. Okay, I mean, so if you see over here in the common source circuit of an NMOS device, so in B you see the DC equivalent of the same circuit. This is the DC equivalent circuit. You see you're going to short this AC source and RG is shorted, so VG is grounded. But then at the source, the drain to source current is being governed by constant current source, which is given by IQ. Okay, so this IQ is going to set VGS. Okay, it's going to determine VGS. The VGS has to adjust itself according to IQ. The idea behind biasing the transistor with the constant current source is that even if the transistor in this case has a, let's say, a conduction parameter Kn, which is, let's say, which has a variation of about plus minus, call it 5%. The Q point is stable. Okay, by biasing the transistor by a constant current source stabilizes the Q point, that is your VDSQ and your IDSQ won't change much. Okay, so even with the change in the process parameters or the conduction parameters of the transistor, you won't have much of the change in IDSQ and IDQ. Okay, IDQ in this case is the same as IQ. So there won't be much change. This biasing the transistor with a constant current source stabilizes the Q point of the transistor. Okay, that's the idea. So even if Kn is varying from plus to minus 5%, VDSQ might vary less than, call it less than 1%. Okay, you see what happens in saturation is that your VGS determines the ID current. So if the transistor is biased in the saturation region, so then ID, the drain current, is given by the conduction parameter Kn, okay, which might vary due to the variation in the process technology of the fabrication, due to the variation in the fabrication of NMOS device. So you have this in the saturation, the drain current given by VGS minus VDN. So the idea is that in the saturation region, your drain current is independent of VDS. Okay, so it's independent of VDS. VDN is a constant. Okay, which might vary with temperature, but Kn has a lot of. It's not only the dimensional parameters in Kn. Kn varies, depends on the mobility. It depends on the other dimensional parameter, thickness of the oxide, capacitance of the oxide. Okay, so if you have this variation in Kn, ID is still ID, which is equal to IQ. For a stable ID or a stable IQ, your variation in the Q point is small. So this tends to stabilizes the Q point. Okay, so you have a stable Q point or stable operation of a transistor if you bias this with a constant current source. Okay, so you have a stable Q point. That's the idea. And then again, you don't need a constant current source. Well, that's how it is depicted in the circuit diagrams. This is also accomplished by what you call it a mirror NMOS circuit configuration. So this is also based on an NMOS MOSFET. Okay, it's not a constant current source. It's again NMOS circuit. So just like you have enhancement load devices. Okay, so a transistor can model a nonlinear load device. Even this load is also MOS load, or let's call it enhancement MOSFET device. So everything is based on MOSFET. Everything is transistor logic. Okay, so MOSFET can be biased with a constant current source IQ, and then the gate source voltage of the transistor in the circuit has to adjust itself to the corresponding current IQ. So once it is adjusted, well, then due to the variation of conduction parameter Kn, you don't have any variation in VDS or IQ, which is set by the constant current. Okay, so to understand how this biasing is done, let's first consider this NMOS current mirror. Okay, in part A you have this NMOS current mirror for an NMOS M1 device. So this is an NMOS device. So M1 transistor is an N-channel MOSFET device. In circuit configuration of B, you see that MA is a PMOS device. You see the direction of the current is the other way around as compared to NMOS. Okay, it's uh, into the source. Here it is out of the source. So, but again, in this part B, the PMOS is being biased through a current source IRF. Okay, the reference. Similarly, over here, this NMOS is being biased by the current source IRF1, and these transistors M2 and M3 have a very similar, just like MC, MB, both are PMOS devices. Over here you have M2, M3, and these are what constitute the mirror device. I mean, the conduction parameters and threshold voltage associated with these two transistors and these two transistors MC and B are the same. So basically, I mean, if you analyze this, if you do the DC analysis, you'll find out this IQ1 will be equal to IRF1. Similarly, IRF2 will be equal to, this will be the same drain current which you will have, which is responsible for biasing of the transistor MA, or the PMOS device over here. Okay, so these two transistors, they form the current mirrors. Okay, so we can implement the current source by using MOSFET devices. The circuit shown in figure 49A and B are the first step towards this design. So the transistors M2, M3, 49. So in this figure 49A, you have M2, M3, which are biasing, which acts as a current mirrors, and they bias the transistor M1. Okay, so they form current mirror, and they're used to bias the transistor NMOS M1. Similarly, MB, MC in 49B over here, MB, MC are biasing the transistor PMOS device MA, or used to bias the PMOS transistor MA. Okay, so the idea is the same. Well, both the transistor M2, M3, and similarly for this MB and MC, you have the gates tied together. Okay, and then the sources are also connected. So for the same conduction parameters, you're going to have the same current. So let's analyze this circuit. I mean, how we say that these are mirror current devices. Let's try to analyze this circuit. Let's try to do a DC analysis to find out how this occurs. So so you see this in example 3.14 from your course text, and the objective is to analyze the circuit of 49A over here. Determine the bias current IQ1, which is here, which is the drain current of the transistor M1. So you have to determine this current IQ1, and the gate source voltage of the transistor VGS1, which is VGS1, and then the drain source voltage of M1. So you need to determine the drain source voltage. So you see this IQ1, IDS1 is going to constitute the Q point of the transistor M1. So let's call this Q1. So let's find out what this current IQ1, VGS1, and VDS1 are. So the given parameters are, we're given the reference current, that's 200 microamps. Okay, so you must notice over here this reference current reference 1 is also equal to, if I must write this as ID3. Okay, because this is the current source which is connected in series with the drain of the transistor M3 over here. Okay, so drain, this is the source, and this is the gate which is connected to the second transistor M2. So the current, this is also the drain current, this is ID3. Okay, so now if you recall in the previous example when we talked about this stabilizing the Q of the transistor, okay, there was an example in the previous videos which we have discussed how employing using constant current source to bias the transistor helps stabilizing the Q for a given variation in the conduction parameter. The transistor was operated in saturation region. Okay, why it is operating in saturation region? It's just there to make sure that the current ID is independent of VDS. Okay, so over here again, we can assume that this transistor M3 and M2 both are operated in the saturation region. Both are in sat regions. Okay, this is sat, and then finally your M1 is also in saturation region. So so you are given this current for the drain current. for the M3 transistor, we are given the supply voltage is V plus, V minus, so this is plus 2.5 volts, and you have V negative minus 2.5 volts. So assume the transistor parameters, the threshold voltage is given as 0.4 volts, and that is applicable to all transistors M1, M2, M3. The general width modulation parameter is 0. That means we are considering the ideal IV characteristics. So I mean you can write this as ideal MOSFET devices, ideal MOS devices. These are not the actual devices, but the ideal MOSFET devices. So you don't have any forward resistance. In the saturation region, ID is independent of VDS. Okay, so it's an ideal device. Sorry, it's VDS, and this is ID. So the conduction parameter is given for M1, M2, M3. Okay, so just for M1 this is 0.25 milliamps per volt square. For Kn2, Kn3, these are for M2 and M3, and given 0.15 milliamps per volt square. The drain current ID3 you see is the same as 200 microamps. Series current, same current. Now, since the transistor is biased in the saturation region, you can use the ideal IV relationship of the MOSFET device, or NMOS MOSFET device, to evaluate what VGS3 is. Okay, I mean the VTN is given. VTN is for your M1 device is 0.25. You can plug it over here. Sorry, you can plug it in KN3. Okay, over here, and VDN is 0.4 volts. That's also given. So ID3 is equal to IREF, which is 200 microamps. So the only thing left out to be found out, is VGS3. Okay, so you reformulate this equation. I mean, this can be written as ID3, or you could bring this down over here, take the square root plus VTN. This gives, you can rearrange the equation as such to find VGS3, and this gives you, just substituting the value of ID3 and KN and VN, gives you VGS3 as 1.55 volts. So you note that this VGS3 is found from considering that the transistor is biased in the saturation region. So once you have VGS3, you have VGS2 as well. Why is that? Because you see the source is common. This is the source of the transistor, source terminal. It's tied up together. The gate is tied up together. You have the same gate. So the transistors are in parallel. They're connected as such that VGS. Okay, once you have VGS3, you have VGS2 as well, which is the same as 1.55 volts. So you can, from the VGS2, you can again use the same saturation region. I mean, instead of saturation region IV characteristics having VGS3 over here, you plug VGS2. You bring VGS2 over here, use Kn2, and find what the drain current is. That is your IQ1 as well. I mean, the drain current over here is IQ1. The drain or source current is the same thing. Okay. So if you substitute this value of 1.555 volts over here, threshold is still 0.4, and then Kn2 is given as 0.15. You find IQ1 as 200 microamps, which is the same as IREF1, reference 1. So you see that the current, the magnitude of the current is the same as IREF1. Okay, I mean the magnitude of the current for ID3 is the same as the current for ID1, which is IQ1. Okay, over here. So these are again the mirror. So we call them the mirror current devices, M2 and M3, which are biasing the transistor M1. Now, since IQ1 is the same current which is going to flow over here as ID1, so you can use this ID1 current to find out what your VDS1 is and what your VGS1 is. So first of all, from IQ1, using the same relationship, because M1 is also biased in saturation region, you can find what VGS1 is, okay, from the same saturation region current equation which we used initially over here. Okay, so this is the current relationship. So just bring VGS1 over here, Kn1, so you just replace this 1, VGS1, VTN1 is the same. Okay, just rearrange the term. So you have this 0.4 over here, Kn1 is 0.25, it's 0.25, so it comes over here. This is 0.2, again IQ1 is 200 microamps, 0.25 is over here, threshold voltage is the same. We find VGS as 1.29 volts. Now since the gate, or you can say that VG is grounded, so VG is 0, That implies that VGS1, which is VG minus VS1, is minus VS1. Okay, so or you can say that VS1 is minus 1.29 volts. Okay. Now you see this current is the same current that flows in the drain terminal of M1. So this, let's call this ID1, and ID1 once again is the same as IREF1. It's one and the same thing. These are the current mirror devices. So let's use this. So you see, if you apply the KVL on the outer loop of this M1 transistor, you have from V positive minus IQ1 RD. So basically this is V positive minus the potential difference of VD1. Where is VD1? Here is VD1. This is your VD1. This node is VD1. So the difference is the drop across the resistor, load resistor RD. So this is RD, basically ID1 RD, ID1 RD. So that's what it is over here. Okay, I mean this equation is same over here. So VD1 is equal to V positive minus ID1 RD. So you have this IQ over here. Substitute the values and you'll find this out to be 0.9 volts. So that's VD1. Then from VS1, so VD1 minus VS1. So VS1 was minus 1.29 volts. So this comes out to be 2.19 volts. That's the other part of the Q point. So this is VDS. I'll call this VDSQ. Okay, so this is VDSQ, and you have your IQ, which was the same as IREF1. Okay, I mean this was ID1, this was IQ1 or ID1, same thing, ID1, or call it IDQ. That's your Q point. So transistor is biased in the saturation region. That's why we are using the current voltage relationships of the sat region. Okay, so you have IDQ and then you have VDSQ. So you have the biasing points. So M1, you can also find out from this VDSQ that this M1 is indeed biased in saturation region. Well, how you do that is that you find the transition point where the transition occurs from non-sat to sat. So VDS sat is given by the overdrive voltage. So VDS sat for transistor M1 is given as VGS1, which is what? Which is 1.29 volts, minus VTN, which is 0.4 volts for all transistors. So this is equal to 1.29 minus 0.4, and this comes out to be 0.89. Okay. 0.89 volts. So this is the point where the transition occurs. But then your VDSQ 2.19 volts is greater than this value. So VDSQ is greater than 0.89 volts, which means the transistor is indeed biased in the saturation region. So yes, you can use this relationship of the IV relationships in the saturation region to find a mirror current. So the idea is that these M1, M2, and M3 transistors, they have the same, for example, conduction parameters. They have the same. I mean, the gate source voltages are the same. Okay, so of course they are going to produce the same current. I mean, in the saturation region, both transistors are in saturation region, and in saturation, the drain current is independent of VDS. You don't need to consider VDS over here. Whatever VDS is, I mean, it's not going to affect the current ID in the saturation region. What's going to affect the current ID is the parameter VGS, and VGS is tied together. So VGS is the same for both devices. I mean, VGS is same for M3 and M2. Okay, so VGS is the same for M2, M3. So that means if VGS is the same, then from this relationship over here, over here, if VGS is same, VTN is the same, conduction parameter same, the current is going to be the same. So of course you're going to have a current mirror. It's like a current mirror. I mean the current over here in the drain current for ID3 and the drain current of ID1, these two currents are equal. These two currents are equal. So this is the idea behind the biasing of transistor. For example, over here M1 by transistors M2 and M3, which form the current mirrors. Okay, so that's the idea. So now, okay, over here the comment says, since the current mirror transistors M2 and M3 are matched, they are identical parameters. The gate to source voltages are the same in two transistors. So the bias current IQ1 is equal to it mirrors the reference current IRF1. Okay, that's it.